Alright, so this is part 4 of stellar structure and evolution. In our last part, we finished by saying that main sequence lifespans of stars are very, very supersensitive to mass, and inversely so, meaning the more massive the star, the shorter its main sequence life. You can think of these stars in the upper main sequence here, the massive ones, as the big gas guzzlers of the universe. These guys live life in the fast lane and die young. On the other hand, these guys down here, the very dim, faint, low-mass stars, they don't have much gas in the tank, but they are very miserly at spending it. They burn it very, very slowly, and therefore they live virtually forever. I mean, these stars down here live so many times the current age of the universe that it's almost not even worth talking about when they will give out, because the universe has to exist for many times longer than it already has for these guys to give out. Our sun will live for 10 billion years, so we're about halfway. We're about 5 billion years into that, and in another 5 billion years or so, the sun will evolve off the main sequence and will become a giant star. But we'll get to that in a few minutes. What I'd like to talk about now is what happens if you have a group of stars that were all born simultaneously, kind of like a litter of puppies. They're all born at the same date. Well, the thing about stars is you don't have many identical twins in that batch. What will happen is, as we saw in the star formation part of the course, is you'll get a lot of low mass stars, you'll get fewer medium mass stars, and you'll get just a smattering of the really monster bright high mass stars. Okay, but basically all of these stars will become main sequence stars more or less simultaneously. Now, I'm not being entirely accurate about that. When these stars are actually more than halfway through their lifespan, these guys down here are still protostars evolving onto the main sequence. But let's ignore that little technicality, and let's just say that all the stars are born at the same time in the cluster, and out of the same cloud of gas and dust, and therefore all have the same birth date. Well, if you followed this cluster over time, and if you could live billions and billions of years, you would find that these stars up here would end up turning into supergiants before these stars were even close to halfway done with their lives. And these stars would just be starting their lives. If you go for 5 million years, let's say, all the stars in this part of the HR diagram would have disappeared and become, well, not disappeared, but they would become supergiants. Perhaps some of them would have blown up as supernovas. We'll get to that shortly. If you watched it for 100 or several 100 million years, then these stars would start disappearing from the main sequence of that cluster as well. And so if you plot the stars of a star cluster on an HR diagram, it'll depend how far down the main sequence that stars are missing. If stars are filled up almost all the way to the top of the main sequence, then you know you have a very young cluster. If most of the stars in this portion of the main sequence are missing, then you'll have a cluster that's about, say, 600 million years old. If you have a cluster that's missing stars all the way down to a solar mass, and they have it turned into giants or supergiants, well, that means that your cluster is about 10 billion years old. And there are clusters that are that old. And so, if we could make an HR diagram of a cluster of stars, and it's a very tedious thing to do, by figuring out how far down the main sequence the so-called turn-off point is, in other words, where main sequence stars are just about to evolve into the giant branch of the HR diagram, that gives us an estimate of the age of the cluster. Okay. So when a star reaches the end of its main sequence life, it becomes a giant. It moves off the main sequence. Now, the star isn't really moving anywhere. It's in the cluster wherever it was, and it's changing into a giant star. But because it changes place on the diagram, we say that it moves off the main sequence. Since stars in a cluster all form more or less simultaneously, we can then estimate the age of a cluster by making an HR diagram of its stars. And basically, we can estimate the age of a cluster. It'll be approximately equal to the life expectancy, that little equation I showed you a few pages back, the life expectancy of stars that are just about to finish their main sequence lives and turn into giant stars. So, for example, we had a 3 solar mass star here. If the turnoff point, if we look at a cluster and we plot its stars, and we see that they're all main sequence stars up to about 3 times the mass of the Sun, an F star, for example, and everything else is a giant star, well, that means that this is the turnoff point. This is where stars are just starting to evolve into giants. And that should be approximately, and again, the age estimates are fairly rough here, that should be approximately equal to the age of, or the life expectancy of a 3 solar mass star. Okay, so the age is approximately 500 million years, maybe 600 million years. On the other hand, if you have a cluster like this, where you only have the lowest part of the main sequence still on the main sequence, and then you have a smattering of giant stars, and you have some white dwarfs even, well, that means that this cluster is extremely old. If it's 1 solar mass is the turnoff point, we know our Sun lives about 10 billion years, so this cluster must be approximately as old as the life expectancy of our Sun, because we know that a solar mass star is just about to turn into a giant star in this cluster. And since they were all formed approximately simultaneously, we know the age is about 10 to the 10th, or 10 billion years. Okay. So that's an extremely useful thing, and we're going to find out in the chapter on galaxies that there are these clusters called globular clusters that are the oldest clusters in the universe. They are somewhere between, many of them are between 10 and almost 13 billion years old. That goes back to nearly the beginning of the universe. Okay, so we talked about main sequence stars finishing their main sequence life and turning into giants or supergiants. The next question we'd like to address is, how does that happen and why does it happen? Well, it's actually fairly interesting and not all that complicated. Okay, so most stars that have masses greater than about 4/10 the mass of the Sun will go through a giant stage when they exhaust all the hydrogen fuel in their core. Okay, so here we have a very simplistic drawing of a main sequence star. In the core, you have hydrogen turning into helium. The outer parts are just inert. They're just sitting there. They have approximately 75% hydrogen, about 25% helium by mass, okay, in the envelope. Okay. Well, as the star continues its life, hydrogen will be turned into helium. The core will grow more enriched in helium, or you could say more contaminated by helium, because helium is not fuel. Helium is basically ash or waste. So the core will be contaminated by more and more helium. As the helium waste builds up, the hydrogen fusion will slow down. And in fact, when the entire core is helium, it will slow to a halt because it's not hot enough to burn helium. When that happens, the temperature goes down because there's not enough energy being created, and therefore gravity starts to win the game again. Remember when we talked about the pressure temperature thermostat to keep a star at its comfort level? Well, the star can't get to a comfort level now, at least not the same comfort level, because it doesn't have any hydrogen left to burn. So the star doesn't know that, so the core begins to contract. The core will shrink, and of course when gas is compressed, in this case helium gas is compressed, it will heat up. The star's core will contract due to gravity. And when that happens, and the star's core heats up, there's a lot of fresh hydrogen out here in the envelope. Oops. There's a lot of fresh hydrogen out here in the envelope that will fill in the gap. Okay, that will backfill where this core is leaving, the area where this core is leaving. Okay, as the core shrinks, the fresh hydrogen backfills the region where the core was, and being in contact with this much hotter core now, what you end up happening is you end up getting a shell of fresh hydrogen igniting in hydrogen fusion. The temperature will exceed 10 million degrees, and therefore you'll get hydrogen fusion occurring in a shell surrounding the core. So you have this helium core that's still contracting and heating up, and then you end up with hydrogen fusion in a shell around the helium core, and that will suddenly pour out lots more energy into the envelope of the star. And the envelope of the star will heat up, and whenever you heat up a gas, it will try to expand, and the envelope will expand outward, and the star will begin to grow, or inflate, so to speak. The star's envelope expands, and that's when a star becomes a giant. Okay. Now, if the core temperature exceeds 100 million degrees, helium fusion will occur. Sometimes that happens when the core is still a nice, well-behaved gas, and other times that will happen when the core is nearly solid because it's so dense, and then you have a more sort of semi-explosive event called a helium flash. Okay, so if the core temperature exceeds 100 million degrees, helium fusion occurs, and you end up with a star with helium fusion in the central core, surrounded by a shell of hydrogen fusion, and a very large bloated envelope. And that's when you get what's called a red giant. Okay. So, having said that, there are stars that will not go through this phase, and those are very, very low mass stars. The exact scenario depends on the star's mass. Okay, so there's several different possibilities of how a star will die. Very, very low mass stars, somewhere between 1/10 and 4/10 of a solar mass, will not go through a giant stage. And the reason is the hydrogen being turned into helium in the core is circulated throughout the star. These stars are convective, okay, throughout. There's this circulation pattern of convection going on inside. The star is like a giant lava lamp where the warm stuff is near the middle, but there's an exchange of material between the central portion and the envelope. And so basically the core does not just run low on hydrogen fuel. The entire star runs low on hydrogen fuel. So because these stars are convective throughout, material in the core is circulated throughout the star, there's lots of mixing. The helium buildup is not limited to the core. The entire star eventually runs low on hydrogen fuel. Okay? So instead of just the core collapsing, instead of just this core collapsing and the rest of the star backfilling in with fresh hydrogen, the entire star collapses, because even though there's a backfill, the backfill has just as much helium waste as the core. There's just nothing fresh to burn. The star contracts as the energy output becomes inadequate to support the star. Okay. The material in the star is compressed to enormous densities. The gases in the star can't ignite in nuclear fusion. There's not enough temperature to keep the star a gas, basically, to keep it from compressing any longer. When the matter inside the star is compressed to an extremely high density, the overcrowded electrons, you can think of these electrons as sort of claustrophobic, hyperactive electrons, they create a pressure to counteract gravity. Okay, this is not because of their electrical repulsion. This is because of a quantum effect where you can't put two identical electrons in the same space, in the same energy level. So some electrons get very, very energetic. And this is something called degenerate electron pressure. When you have degenerate electron pressure, you can think of these electrons inside the star as being put into tiny shrinking prison cells. And as they do, some of the electrons get extremely energetic, bouncing off the walls of these prison cells to keep this little prison cell from collapsing any further. Okay? And this is something called degenerate electron pressure, and the star is then called a white dwarf. Okay, so a white dwarf is a star that started out with a mass like a star and is now the size of, say, the Earth. Okay, we will continue with this in part 4. Oops, part 5.